Let H be a Hermitian matrix, whereby Hermitian we mean that H dagger is equal to H itself, and by dagger we mean complex conjugate of H followed by the transpose of that matrix. So complex conjugation followed by transpose is denoted by the dagger operation, and if the dagger of a matrix is equal to itself, then it is said to be Hermitian. So H is our Hermitian matrix, and we want to show that eigenvalues of H are real. So suppose lambda be an eigenvalue of H, and corresponding to this eigenvalue X be the eigenvector. So X is eigenvector and lambda is eigenvalue. Since X is eigenvector corresponding to eigenvalue lambda, so X first of all must be a non-zero vector. By definition of an eigenvector, X must be non-zero. So the norm of X must be greater than 0, and norm of X, the square of the norm of X is simply X dagger X. So X dagger X must be greater than 0 because it is a non-zero vector. Now since lambda is eigenvalue and X is eigenvector, a non-zero vector, we have this relation H acting on X will be equal to lambda times X. This is simply by the definition of eigenvalue and eigenvector. So H acting on X will give us lambda times X. In this equation, if we multiply by X dagger on both sides, we will get X dagger Hx equals lambda will come outside and we'll have X dagger X. Let us call this equation as 1 and let us call this equation as 2. So we have obtained the second equation from the first one by multiplying both left hand side and right hand side with X dagger on the left. Now in equation 1 we take dagger on both sides. If we take dagger of Hx from 1, we take dagger on both sides, Hx dagger, this will be equal to lambda X dagger, but lambda dagger will be simply its complex conjugate, so lambda star X dagger, and Hx dagger will be X dagger H dagger, and this will be equal to lambda star X dagger. But since H dagger is same as H, so this will give X dagger H equals lambda star X dagger. Here in the second step, where we write Hx dagger equal to X dagger H dagger, we have used this general fact that AB dagger is equal to B dagger A dagger. So we have used this relation in the second step. So we have arrived at this equation by taking dagger on both sides of equation 1. Now in this relation we multiply by x on the right side. On both left hand side as well as on right hand side we multiply by x. So we will get x dagger hx multiply by x equals lambda star x dagger x. Let us call it equation number 3. Now if we subtract equation 3 from equation 2, then on the left hand side both these equations have x dagger hx, x dagger hx. So on the left hand side we'll get 0. If we take 2 minus 3, equation 2 minus equation 3, then on the left hand side we'll get 0, and on the right hand side we'll get lambda minus lambda star x dagger x. But we already know that x is an eigenvector corresponding to eigenvalue lambda, so its norm square must be greater than 0. It is a non-zero vector. So this implies, since x dagger x is greater than 0, this implies that lambda minus lambda star must be equal to 0, which implies lambda must be equal to its complex conjugate. Therefore, eigenvalue, we assumed lambda to be any arbitrary eigenvalue of h. So this implies that eigenvalues of h are real. So if we have a Hermitian matrix, then its eigenvalues are all real.